This morning we will look at the second method for solving nonlinear equations. Okay, and this method is a Newton-Raphson. Newton-Raphson is used to solve nonlinear equations. Okay, and but it has some different features from the bisection methods. Okay, and as we will see now. Okay, let's begin with how can we develop a Newton-Raphson. And here we suppose that x star is a root of the nonlinear equation fx. Okay, equal to b. Oh, sorry, fx equal to 0. Then we can, okay, then we use the Taylor series at the, okay, and okay, and we suppose that xk is a current is a current iterate. Oh, okay. Let's look at this figure. Okay, the xk, let's say xk is what we call a current iterate. Okay, in iterative method, okay, we generate. Okay, let me explain. Okay, before we maybe it's a good idea to give you the meaning. Okay, to give you the meaning of iterative method. Okay. In iterative method, in an iterative method, we start with x given an initial point x naught. Okay, in iterative method, given an initial point x naught, we generate. Okay, given we generate x1, x2, and so on. Okay, so this is actually, we can write it, this is a sequence. So start giving an initial point x naught, we generate a sequence of point until xk is close to a solution, until xk converges to, okay, until xk converges hmm? Hmm? To a solution x star, or until the iteration is terminated. The iteration. Oh. Hmm. In an iterative method, okay, I summarize again. In an iterative method, we start with an initial point x naught, and then we generate a sequence of points x1, x2, and so on. Okay, until the iterate xk converges to a solution x star, or until the iteration is terminated for another reason. Okay, for example, if it for example, it's the iterations doesn't seem to converge. Okay, and then for many iterations, then we decide to stop. Okay, before the iteration gets into an infinite loop. And and how can we know that x converges to xk converges to the solution x star? So we see the difference if xk is close to xk plus 1, then we decide to stop. For example, if the xk if xk plus 1, okay, which is called the next iterate, xk plus 1 minus xk is less than or equal epsilon, where epsilon is a small number, or xk plus 1 minus xk divided by xk, okay, is less than. Okay, then we decide to stop. Okay, that's the idea of an iterative method. How an iterative method looks like. Okay. Now here we come back to Newton-Raphson. Here we suppose that xk is a current iterate. Okay, and then we here. Okay. Then we want to move from xk to we generate xk plus 1. So the difference between xk and xk plus 1 is s. So sk. So we can write. So we arrive at a recursive formula: xk plus 1 equals xk plus sk, where sk is what we call as a correction term. Okay, and we will see what is the correction term for this problem. Okay. Now we consider the Taylor series at the point, the Taylor series of the function f at the point xk. Then what we have is fxk plus s is approximately equal to fxk plus s multiplied with f prime xk, right? This is the first order. We used a first order Taylor series expansion of the function f at around the point xk. Okay. Then now we put on and we add another assumption. Suppose xk plus 1. So suppose xk plus s is a good estimate of x star. Now that means if xk, okay, that is xk plus s is approximately equal to fx star. Okay, so that fx star or fxk plus s in the above expression can be set to 0. Now, now you can see that with this assumption, then if f prime xk is not equal to 0, okay, then we are able to solve the correction term s, which is s is from this linear equation. This is a linear equation, and then we solve s. Then what we have is that the correction term s is equal to minus fxk divided by f prime xk. Okay, and from this, then we write the Newton-Raphson formula. Okay, the equation 3.2 is known as a Newton-Raphson method for scalar nonlinear equations, or the scalar version of Newton-Raphson method for solving nonlinear equations. Now, in the next example, we will illustrate how to use Newton-Raphson. Okay, so we apply this to the same problem as last time. We compute the square root of 2 by Newton-Raphson method. Now, now we choose a function f. Okay, so now you see that x2 square root 2 is a root of fx, which is equal to x squared minus 2, right? So this is the nonlinear function we choose, the same as last time. Okay, so and the square root 2 is the positive root. So this equation has two roots. It has okay at what we want to compute is the square root 2. Okay, the square root 2. This okay. I think in the homework I'll give you okay, in the homework 1 I will ask in one question. I ask you to prove, okay, for a similar problem like this, the iteration can converge to either the positive or negative root depending on the initial guess or initial point x naught. Okay, but in this in this example we skip that explanation. Okay, just for we focus on the method. How can we do this first? When we use the Newton-Raphson, we use the positive. Okay, we find the derivative, as you can see from the Newton formula. To do the iteration, we need to know fx and fx prime. F prime x. So we need to know not only the function f, but also the derivative of the function f. So in using Newton-Raphson, we need to know not only the function f, but also the derivative f prime of x. And this is different from the bisection. In the bisection method, we need only to know the value of the function f, right? And in so we form the formula, okay? Fxk as fxk plus 1 equals xk plus 1 equals xk plus xk plus 1 equals xk minus fxk divided by f prime xk. Okay. Then we substitute fxk and f prime xk in the formula, and then we obtain this. Okay. After rearranging the formula, then we have a simpler one. We have this. So this is okay. We tidy up it a little bit. Okay. Now this is the formula we will use in the following iterations. Okay, so we start with x naught being 1. Then we do the iteration, the first iteration. The x1 is 1.5. Okay. And fx1 is 0.25. And then this is still not close to the solution, right? Because we already know the square root 2 is approximately 1.4142 something. And then we do another iteration. We do another iteration. Then x2 now is 1.41666666, right? And then fx, you see that fx2 now is reducing. Okay, now it's reducing to okay, to 0.00694, right? Then we do another iteration. You see that you see this, okay? The absolute value of xk plus 1 minus fxk, okay? And to see whether this converges or not, then there are two indicators for this. First, you can see that you can examine the absolute value of xk plus 1 minus xk, or the absolute value of fxk, right? Because at the solution, we know that fxk plus 1 should be close to 0. Okay, then you can see that we can use these two expression to form a criteria for terminating the Newton-Raphson. And sometimes some people might prefer using this, okay, the relative form, the relative error, instead of the absolute error. Okay. Or okay, when we look at the absolute value of the error, sorry, when we look at the error in relative form or the absolute form, okay, the meaning, their meanings or the purpose of using them is slightly different depending on the situation. If the solution is, I think maybe for the error, sorry, for the error, no, we don't use this because we know that it's already is close to zero. Oh, sorry, yeah. If we look at the iterate, okay, and we look at the iterate at this one, okay, just this one, this is the absolute. We look at the absolute error, whereas this is the relative error. Okay, when we do the iteration in a good in a good software, okay, we don't choose to use any only one of them. We use both depending on the situation, and sometimes okay, a user can the user can make a choice, can make that choice, okay, can make a choice whether to use this or that, the absolute error or the relative error to terminate the iteration. Why? Now can you see the difference, Thanapon?
Yes.
Can you see the difference between uh, uh, the two forms? Are they different? Oh, of course, the form is different, but um, do both of them give different consequences?
If AK is equal 0.
No, if the
Or
solution, is
if there's
close to zero.
close to 0.
You see that we
Then
don't. Yes, good. You see the difference is in the absolute form. Okay, when we look at the absolute error, then this is good if the what? If the solution x star, okay, is close to zero. If the x star is near, has very okay, but then in the relative error, this is good if we use if the x star or the solution is not close to zero. You see that, for example, if the solution if the solution x star is, let's say, 1000, right? When we look at the absolute error, if you specify the absolute error like 10 to the power of minus 4, then then that means if okay, if we set the epsilon to be 10 to the power of 4, then you see that the difference will occur, okay, if the iterate, if the two iterates are different in the how many digits of that, in the 7th or 8th digits, right? Then it will stop. Whereas if we use if we use the relative error, we set with the same epsilon 10 to the power of minus 4, right? Then you see that if we need the accuracy within 0.0, let's say within 0.01%, right? Then you see that the iterate will stop, okay, when the xk plus 1 and xk are accurate up to the 4th significant digit, and then it will stop, okay? the two forms are very different, and okay, from this point of view. Okay, in this example, okay, now you see that in this example, Newton-Raphson converges very nicely. Fortunately, this example, Newton-Raphson converges very nicely so that you can see that, okay, this is a good method, but this is only one side of the coin.
Excuse me, Ajahn.
Yes, sorry.
Ajahn, the initial guess, do you get to decide to take any initial guess or you'll be given?
Sorry, could you say again?
I mean, how do you get to take the initial guess, the at S naught?
Depending on the problem. Usually, I think when you well, when we solve this in real applications, you should know roughly where are the initial points. Sometimes we don't know, okay, but in some example, but you see that in this example, we know that square root 2. We have to consider that from the properties of from using physical properties of the problem. Okay, in this one, we know that square root 2 is between 1 and 2. Am I right?
Yes, Ajahn.
Yeah, so you can choose x naught, something between 1 and 2, for example. Or in power system, when we solve the load flow equation, okay, some of you may have heard of the load flow, okay, load flow. When we solve the load flow analysis in power system, when we consider load flow analysis, we know that the voltage at the bus, okay, the bus voltage should be it cannot be very slow. Oh, sorry, it cannot be very small, like 0.1 pu. This is impossible, right? Because I think when we run the load flow, the system operates in a normal condition. So the voltage, the bus voltage that we want to solve should be about it should be 1 plus or minus 10 or 20%, right? So we start with the bus, the unknown voltage, bus voltage as something between. I think normally people use 1, okay, and then the angle of the voltage, it should be somewhere not more than it's not 90, not close to 90 degrees. Okay, and then they start with the angle voltage 0. That's an example. Or when we solve when we solve these DC circuits with nonlinear elements such as diode, and sometimes I think we know some from the property of the electronic circuit. Then we know some the value of the voltage. For example, the voltage across the diode when it's on, it should be it's close to 0, right? I think, or 0.7, for example. That's from the PN junction. Then from that we know, right? So we know initial points. This is the real situation. Is that okay, Emmanuel?
Yes, Ajahn. So
Okay.
whatever initial guess we take would arrive at the same convergence or close to.
Sorry? Can you say again?
Said it's clear, Ajahn. I said, does that imply whatever initial guess we take, our solution will converge at the same point?
Okay. Yes. Okay. Okay. Right. I have a problem with my pen. I think I have to change the pen. Okay. Just wait for a moment. I need to change to use another pen. Because okay. Now, okay, if is there any question regarding doing the iteration in the Newton-Raphson? No, right? Now you see Newton-Raphson is converges very fast if it converges. However, the Newton-Raphson does not always converge. Okay, this is the well-known fact. Then now, okay, next we will consider the how the behavior, the convergence behavior of Newton-Raphson. Then we look at the geometric interpretation. Okay, this figure actually comes from National Software. You can see if you look see the text National Software, you will see this. Okay. Oh, again, when you read, I think for this chapter, I suggest you read National Software chapter 2 on the set, okay, on the section nonlinear equations. Okay, the details are in there. Okay, now when we okay, now here we want to look at the interpretation of Newton-Raphson. Now let me remind you again what is we generate the Newton iteration is xk plus 1 equals xk, okay, minus f k divided by f prime xk. Okay. Now, now look at this figure. This figure we have the graph of the fx intersects the x-axis, right? And where the graph intersects the x-axis, that's okay. The, this that's where the solution is. This is the solution. Okay. Now, suppose we start at the iterate x naught. Okay. Then at the coordinate x naught f x naught. This point is the coordinate, right? This is the point at this is the coordinate x naught f x naught. Okay. Then at this point we draw the tangent line to intersect the x-axis. Okay. At this point we have the x1. Suppose we don't know what x1 is, okay, at the moment. Suppose we don't know what x1 is, okay? We will find that. Then, so, and we consider the triangle. this triangle, in the yellow triangle. Okay. From this height is equal to the f, right? This height is equal to fx naught, right? This is fx naught. Okay. And the slope, what is the slope of the tangent line? The slope of the tangent line is equal to f prime x naught. Am I right? Am I right? Okay. Here you will see that this is, suppose we call this S. What S is? When we look at the, okay, from this, you see that x1 is equal x naught plus S. Nope. Minus is x naught minus S, right? Right, Emmanuel?
Yes,
Is that right? Yes. Okay. So when we look at this triangle, then you'll see that S is equal to, what is the value of S? S is equal to, we use the tangent of this, right? It's angle theta. And theta is equal to F. Tan theta is equal to Fx divided by S, right? Correct?
Yes, okay. In this case, is it not f prime?
And this is equal to, yeah, that's right. And this is equal to F prime x naught. That means S is equal Fx naught divided by F prime x naught. Right. So this is it. I think we write it on the other side. So F is equal to, obviously, F is equal to Fx naught divided by F prime naught, right? So X1 is actually the X1 obtained from the Newton-Raphson formula. So that means when we do in the scalar case of nonlinear equation, when we do the Newton-Raphson, we can do that. This is by in computation, right? This is by computation. But then if we do that graphically, then that means at the iterate xk, okay, at the iterate xk, then we draw the tangent line to intersect the x-axis, and where the tangent line intersects the x-axis, and that is where the xk plus 1 is. So we obtain the xk plus 1 from this, and then we do it again, right? So you see that if we do this graphically from this figure, we know that the Newton-Raphson converges to the solution, right? Okay, we know that it converges to the solution, and let me write something on. Okay, now if now, you see that this is Now we go back to look at the example of fx equal to x squared minus 2. Okay, when we solve this, when we solve the positive root, what is the graph looks like? What is the graph of x squared minus 2 looks like? Joe. Thanapon, can you tell me?
It's parabola
It's a
intersect
yes.
intersect x axis at
This is a parabola, right?
yes,
Then
intersect x axis at square root
so the
2.
graph intersects the x-axis at the on the left-hand side is minus square root 2, and the on the right-hand side is minus 2, right? Sorry, a square root 2. Okay, so this is it. This is it. Now look at this. When you look at this, right, graphically, then you will see that if the initial guess is positive, if the initial guess is positive, then suppose the initial guess is on this side. If the initial guess is larger than square root 2, then we know that it converges like in the previous figure, right? In like this, it converges. Like this figure, it converges, right? Okay, but now, and let's see when the iterate is between 0 and square root 2. If we iterate xk, if the iterate okay, if x naught starting from here, then we know that it's converging. Okay, then now if the iterate x naught, if we start from somewhere from here, what happens? If x naught is between 0 and square root 2, then you will see that what happens? Then you will see that it shoots to goes like this. Oh, this coincident. Okay, it goes like this. Then we have x1, and from x1, then it again. So then you see that if x naught is greater than square root 2, then the Newton-Raphson converges to the root from the right hand side of the solution. But then if the iterate xk, if we start in it, if the initial point x naught is between 0 and square root 2, then the iterate, okay, it gives the iterate the next iterate x1 on the right hand side, and again, and the convergence will be on the right hand side of square root 2 as well. So okay, and this is how we find this. Naught, if x naught is greater than square root 2, then Newton-Raphson iteration converges to square root 2, okay, on right hand side. And if on the other hand, if not between 0 and square root 2, then Newton-Raphson also converges to square root 2 on the right hand side. Yeah. And this is what we see. And if we do that for the negative starting point, then you will see that all the Newton-Raphson will converge to the negative root if x naught is negative. Okay. This is the and so the graphical interpretation is very useful and help us. Okay, it helps us to understand the convergence of the Newton-Raphson. Now, okay, in this exercise, I give you another function, which is the function hyperbolic tan of x. In this, you will see that sometimes the hyperbolic tan, okay, x sometimes the convergence depends on the x, the initial point x naught, and there is a certain okay, for some initial point x naught, the iteration does not converge, it diverges. It diverges, and you will see this. Okay, I'll give you this exercise because otherwise we'll spend too much time on the lecture. And okay, and this is why I give you some exercise. That means for exercise, that's the suggestion. Okay, for you to consider. Okay, after the lecture. Now we look at another one, which is called a secant method. You see that the burden of Newton-Raphson is that we need to calculate the derivative. Is this a problem? Yes. In real application, you see that in real application, if you have analytical expression of the function f, there is no I mean, we can compute f prime very easily, right? If when f prime x is easily obtainable. However, if an analytical expression of the function f is not known, and this is most cases in real application, in any practical application. In many practical applications, okay, f is known as a the black box, right? In load flow analysis or in electronic circuit, okay, when we solve the circuit, we know, okay, and you see that what I mean by this, in many applications, what we know is that we have a function. This is like in a function or a module. Okay, we given x, we can compute fx. given x, we can compute fx, and in real application, and like in the load flow analysis, okay, we form the network equation, and once we know the x, the vector x, or then we compute the fx, right? And we don't, and so in this way, we don't have in this situation, we do not have analytical expressions of the function f. So to compute f prime, we have to use, to compute f prime, we need to apply some approximation. And in the approximation, okay, we compute the function f for many value. We compute f for many, okay, for a few values of x of the x, all right, to estimate the derivative. Now this is what we do in computation, right? And then and this also the need for the derivative is the the need for the derivative is the burden of the Newton-Raphson method. So and then people try to avoid to solve this, right, by we approximate, we add some idea, and then we that is we try to approximate f prime. I'm sorry. We try to approximate f prime xk with xk and xk minus 1 from previous iterations, and that's the idea, okay? And when we apply so f prime xk, we approximate f prime xk by fxk minus fxk minus 1 divided by fxk minus fxk minus 1. You see that this assumption is true, okay, or reasonably true when xk and xk minus 1 are not far away. Okay. Then we substitute this into the Newton-Raphson formula. Yeah, right? And then we have a formula which is known as the secant formula. And the method is called the secant method. So you see that this is the secant formula. Okay, fxk plus 1 is equal to xk plus 1 equals xk minus this. In this, okay, in the second term, there is no derivative, right? There are only fxk minus 1, and okay, right, and xk minus 1. So from this, then we can do the iteration, and from this, when we applied the secant method, okay, I'll let you do at home by yourself. You will see that the secant method is a little bit slow. Is a little bit slower than Newton-Raphson. Okay, and it shares with the Newton-Raphson that it may or may not converge to a solution. So it can converge or it can diverge, depending on the initial point. Okay, but then when it converges very fast as well, but just a little bit slower than Newton-Raphson. Okay, but I mention here because we don't emphasize the secant method now in this, right? We only emphasize we focus our attention only to the Newton-Raphson, but I mentioned the secant method because we will use the idea of the secant method in developing an approximation of the Newton methods when we solve optimization problem. Okay, that's why I mentioned it here. Now come back to the convergence of Newton-Raphson. Maybe it's not, we don't have the time for today. We have to, okay, we will talk about that in next week on Monday. Okay, so the next lecture will be the convergence of Newton-Raphson. Okay, today I'll stop the recording first.